Okay, so use your command the window interface. You can do this simple calculation, and it's like calculator, and you immediately get the answer, and the answer become a variable name called NS is by default, and you have a 3 as a result. And you can assign the variables by give variable name and also the value. Say I assign 1 into A, and then assign 2 into B, so I can do A plus B. All right, so that's a program. Okay, so MATLAB is designed for easy manipulation of vectors instead of only this called scalar, the single value, like something like this. MATLAB is really good to combine this type of values, okay, something like this. You just type that in, and then you create a vector. So now look, this A is a vector, and then in workspace, you have this, all right? So there's a list of values. So you take the whole vector as a object or a variable or sum of the data points. You can think about this. And similarly, if you assign, and in this case, I do B equals A. So I basically copy everything from A and then put into B, assign to B. And also, if I decide to change something, I select number index, say 1, 2, 3, 4, 5, number 5. So that's, I'm going to change the number 5 into something else, okay, to 15. Then you will realize I assign a new value into one of the element in this vector. Okay. Are you with me, everyone? This is straightforward, right?
Yes.
Did you type those and give it a try? Or is it just too simple? You think we should jump to some more advanced? Let me know.
I think this is a good introduction, and everything's been working so far.
Okay. As a good place, you may want to do something like this. If I do DOC, this will bring a documentation of MATLAB. Let me make this font bigger. Go here. Maybe easy to see. So doc, by the way, you do this will CLC will clean your command line window, and but everything is still kept in the workspace. This is still here, okay? And you just clean this. The doc will return, it bring up the documentation. That's a good place where you can start using MATLAB. Simulink is a independent, isolated product, and we don't use that much in biology, in bioinformatics research, because it requires specific type of the modeling of the path interaction between different objects. So we will focus on MATLAB. Okay. There are this commercial package, so everything is well documented, has been rigorously tested by their internal tester. I believe there are a lot of them. So it's really high quality. And on your left, this panel, you'll see a lot of different categories of application areas. You have 5G toolbox, so all the functions related to the development of 5G technologies in there. So MATLAB itself has an independent product. It's a base of a lot of other those packages. So this will be something you will try to get in. And later, if you feel interested in, you can click on, for example, Bioinformatics Toolbox and see what kind of function it provided under this toolbox. Another commonly used for bioinformatics is the one called statistics and machine learning toolbox. So we will use a lot of function in here. Okay, because we are going to do statistics on the data we collected. Okay, I would see this will be number one use for package. And then bioinformatics maybe is another, but currently bioinformatics toolbox doesn't have any single cell related functions. And because single cell data is so new and they haven't been able to catch up the frontier of research in biology, there are lagging time between the new development of technology in biology and informatics tools mature enough for them to develop a function for it and then release as a product. So you don't see much there. And we will start from a very basic in the MATLAB. So click MATLAB or similar as click this icon, you will have this page. And I suggest you use some of your time offline and to do this get started yourself. And then you can move to the language foundation fundamentals. And then more interestingly, the graphic function will be easy to follow because they are visualization. I don't know in the mathematics, I haven't clicked this. So there are basic elementary math, linear algebra. Yeah, I think we will mention some of this because they're very important for data mining, for machine learning. This is the basics. Okay, so I will lead you through some of this getting started. Okay, I already mentioned this desktop basics. And then very quickly, we have a matrices and arrays. Okay, in MATLAB, so arrays is the vector I talk about. They call arrays, and the matrix will be the two-dimensional. So if you have a say A equals 2, 2, 3, 4, then you put a semicolon to separate to make a new row, and then you have a 4, 4, 2, something like this. Then you create a matrix. This is a 2 by 4 matrix. Okay. So you may have a question. So if I miss one of the elements, what will happen? So what do you think?
I think that maybe it'll create the matrix, but there will be an empty value in that.
Yeah, that will be ideal, but in reality, when you type that in, it give you an error message because there's a mismatch between the number of dimension you put in. So yeah. So I will rather put something like this. All right, so this is a very simple idea, and why this MATLAB is useful for biology research, because in the biology research, you summarize or you collect your data. Oftentimes, you can put the data, raw data into a like Excel spreadsheet. Excel spreadsheet itself is a matrix, right? And then so if you can load that information into a matrix like A here, so this A may contain hundreds of thousands of rows or columns, but in the same way, you can easily to manipulate A as a just a single variable. For example, if I do create a B, allow A plus 1. So this is simple operation will allow me to add 1 to each of these elements without doing any looping or individually collect these elements and add 1. But because MATLAB is treated the whole variable as a single entity and then plus 1 for each element of there. So you can do this very easily, and this is kind of a manipulation of the information. And you can extract the columns by, see, I want to the third columns of the information. So in this way, I just extract sub matrix, or in this case, is a one-dimensional matrix, is an array or called a vector. I extract the third column out. Okay, if you try to 3 and 4, the 2 columns, you can do this. So that's kind of operation you will learn if you go into this array indexing. Array indexing tells you how to use these numbers to locate the values and then extract them, or sometimes we want to replace them. For example, if I replace B, the third column of B with the second column of A, so I can assign this part to B, and the B will change the value of this third column and copy from A's second column and put in here. So you can see this kind of manipulation so handy that you can easily to manipulate your data. In this example, there's only 2x4 matrix, but in a large data set, you may have hundreds of thousands of columns, rows. You just do the same, and without even to remember anything, and you don't even have to display anything on the screen. You just do semicolon at the end of the command. The output, the feedback will be surprised, and then nothing will be displayed on the screen, but still the operation already done. So any questions so far?
Don't think so.
Okay. Yeah, so other languages also have a similar kind of operations in Python and R, just in the different flavors. And remember, when you scale things up, MATLAB will be easy. You handle them more efficiently than other languages because it has been already optimized. It take care of the large scale operations. And I know, at least in R, when you have a large data set, it will be very inefficient. R actually borrow a lot of C source code to handle this when the data set become a little bit larger, but MATLAB itself, the native language, will handle those very easily. So this is called a high performance, high level, and because you don't have to do a lot of detailed coding, and you don't have to loop through the steps between different positions, assign value one by one, and you just do this high-level operation. Okay, so workspace variables means something here, and you can preview or get information if you have a long vector, say I create a random number with 3,000 rows in the one columns. So you just cannot display all the values here. So the values here will be showing as a dimension, the number of dimensions, and also the types, the type of the variable. So what we can do is double click this, and you have a preview of what's in this vector. So this is a long list of the random numbers generated. Have you tried this? Do you see the same number I generated? Do you see the first number 0.8147? Do you feel comfortable about this random number?
How do I open up the results? I can't find where to
You
see
have
the
a
random
C, you
numbers.
have a C here. Do you have a C? You double click this.
Ah, okay. Yeah, it's the same random numbers.
Yeah, it's the same.
Yeah, so the reason we although we are using different machine and generate a same random number, because this algorithm generated number, it's a so-called pseudo random numbers, and their algorithm to generate this looks like a random, but they are not actually. It's not a problem. Okay, so this is a numerical algorithm problem. So people use this, if you use similar same random number generators and use the same number of seed, and you generate the same series of random number, pseudo random numbers. Okay. There are certainly we can handle text and characters. Okay, if you have a variable called d, and then you use double quotes to get this. This is a string. Okay, so you get a variable named string. You can handle the string as what you did for the numbers. So you get a list of a vector of strings. So actually, I use this to keep a list of genes, and the gene have a name, ITP8, and then GIP, and then, so you have a name of a gene as a string. So I keep that gene list as a string of array of strings in this way. Yeah, so you can do the first string and the second. So you extract the different position of the string from a different position of the vector. All right. I already said there is basic operation, and then you can start to use functions. So if I have my A here, if I want to do a min, so I'm calling a function. This function will take one input variable and compute and give me the answer. So this min is which min, and I can find where this min is located. So min is a file defined in a so-called function defined file, and okay, it's located here. So once you start to use the min function, MATLAB will start to search for the function called min in the searchable pathways, and then locate it, and then use the function defined in this min to take the input and give you the output. All right. So the median is another function, right? So here we are calling the function other people developed for us. So this will be very useful because we will extend your capacity from a basic operation of this kind of indexing or simple operators, do this plus, minus. But you extend your capacity by using the third-party function other people developed for you. Of course, if you want to do the same, you can do, you have A, then you do the sum of A and divide by the length of A, then you get the mean, which is same as what you have, but you just use different functions here. If you don't want to use, you can use say 1 plus A plus A2, A plus A3, A4, A5, A plus A6, and then you divide by the 6. Okay, so there are different ways you can use off-the-shelf built-in function to do this. You can use some combinations of the simple function to achieve the same goal. Or if you want to use very basic operations, you don't want to use the sum as a function. You just add them up yourself and divide by this, you get a mean. So that's the different levels of the implementation of the same algorithm or to achieve the same operation. Okay, 3D, 2D plot. I will show you if I decide to plot. So A, I have a x-axis is 1, 2, 6, and then my A has values, right? My A have gave me the value for the y-axis. Then I want to use the line dot. So that's a plot I will generate. Can you see from your computer to see this? Maybe not clear. So that's x-axis. You have a 1, 2, 3, 4, 5, 6, and then the y-axis is given by the element in the same order. So my A is 1, 2, 3, 1, 2, 3, 4, 1, 2. Is that correct?
Yes.
Yeah. So if I plot my random number, I remember I have a C. So I just ignore even for the x-axis, automatically give me this. So that's my random number. So you can see this random number have 3,000 of them, and it's distributed between 0 and 1, right? If I generate another random number, say I use random, this time I'm using random n, this will be also 3,000. Don't want to print them out on the screen because there's 3,000 values. So I can plot my original C and then hold on and then plot my second C Okay, in this way, I will superimpose the second curve onto the first. Yeah, so my red curve is C2 generated. Okay. So maybe I should plot C2 first, then C. Those C2 have much larger variance and cover the C. Okay. So my blue line is from C2, which is the normal distributed random number, 3,000 of them. So normal distributed number is between normal distribution have a mean at 0. So you see the blue curve on average is around 0. And then you have a normal distribution. So the standard deviation is 1. So by some probability, you get a really small or large number. So it's like a -3.7 because by chance you should have some of this, but the majority of them it would be around 0. And my original random number generator is a random number between 0 and 1. That's where this orange line is indicated. Okay, with nothing above 1 and lower than 0. So this is 2 random number generator functions, random n and random itself. So this also gave you some idea how you plot the values and to visualize them. So this is just one way to do it. Yeah, I think I will leave this for you so you can write something here and also save them into a file so you can use them later, either as a transcripts or you can develop your own function. So I will leave this for you, and I will give you the rest of the time to until 3 to go through this and ask questions. So next hour, we will have a new student come in, and then we should go ahead and try to download the package I developed, and then you can have a quick start. Okay, even though you may not even have the basic programming skills, but you still be able to start to use the function I already created. Okay, there are many different tutorials and videos available here to help you out, just like what I'm doing right now. And yeah, so there's a rich information, and it's very important for you to have a from 0 to 1 step, and then you can start to build up the power and gradually make it higher. All right, let's take a break and come back at 3.
Sounds good.
Okay, I hope you are back. We will continue, and instead of a progressively, we move forward. Let us just jump in directly to the analysis itself. Okay, we can do this because the toolbox developed for single-cell RNA-seq analysis has been matured enough, and compared to previous group, and you have background in knowledge about the next generation sequencing, and maybe you know what the mapping is. So let's start from a real data and then example data, then we see what we can do with the data. Okay, so let's first download the package and then you play with example data inside the package.
How do we download the package?
Yeah, so start your web browser, one of your favorite web browser, then search scGEAToolbox. So this this stands for single cell gene expression analysis toolbox. In Google, the first hit should be the link to the source code of this. That's where we are going to use. Let me know if you're on this page.
Yep, we're on it.
Yes.
All right, Aubrey.
Yes.
Okay, good. So this contains all the source code and the I'm still updating it. So you see 2 days ago, still working on. So this is a keep updating. So let's browse through to the very bottom because you don't want to download independent function, but you can click in if you are interested in say what's inside the M file. Basically, this defines the function of the file. So you just browse down and to the documentation. So that's what the link I want you to click on. So if you click this documentation, you should see this page. And with this fancy color, I really like. Let me know you're on this page.
Yep.
Yes.
Okay, good. So we certainly can download the zip file, unzip, but I already made it just one step, then everything will be fine. And then click this, get started with scGEATor because it's a scatter plot with function and function. And then there's a section called the quick install. All you have to do is just select this, copy. I select this block of code. What this will do is just to go to this web page and download a zip file from the GitHub, the page I just showed you, and unzip to your local folder and add this folder into the search parse. Then you have everything you need to start to run. And then after you add this parse, I will check, see whether this function already reachable from the command line. If yes, then I just display you already installed that. So what you can do is just copy this, okay, and go back to your web command line window and just paste here. And then you just wait. I'm not going to do it because I already have that installed. But you can just copy that and then paste here. It will take up to 1 or 2 minutes. Download the file, unzip it, and then we are done.
Mine said it installed.
Okay.
Mine just finished installing as well.
Sounds good.
And mine did too.
Okay, then so now if you tap CD gene expression A, so this is a small function. It's just a helper function to change the current work folder from your current folder to the folder which I would like you to be in. Nothing fancy, just change the working folder to there. If you finish this correctly, you should see now the current folder looks like this. That's where the toolbox is installed.
Yep.
Yeah, in my computer, I installed on the E drive under here, but on your computer, probably in the C drive somewhere. Okay, so that's where the package, so you are done with the installation. And then we can load an example file. So load, then you are going to load a file which under this folder. Okay, so all I have to write is example. I press tab and give me suggestion and see a lot of files I can load an example. Yeah, so you can type that in, or if you know how to use the tab key, and then you have the suggestion of the auto completion of those keywords, and then you click return because I already had made this available for you, which inside this file. After you load this, you will have an X and you have a gene list. So that's our raw data. All you need to have is these two files, two variables.
I see him on mine, so I think we're good.
Okay, so this big X is your gene expression data from 8,842 genes in 1,567 cells. So if you double click it, you see this.
Yeah.
If you double click a gene list, you see the name of genes. So the dimension of the number of genes match the rows of X, right? So that's two variables we need. You may have a question about how did I get the information into here? There are tutorials in here, for example, case studies, where to download the data. I download the data and then how to process the data. You have a matrix file, you have a feature. This feature is the gene list. Okay, so where that's, for example, I download the data from a geo database, contains the matrix file and the list of genes. That's the file I download. And then you can get into them, read those files into X and gene list. That's where the file get parsed and then read the matrix in. All right. So if you want to do this, you can copy the code, the broker, this code, you can do this. But anyway, so just assume you finish this, and we have X and the gene list in our workspace right now. So that's what you see. You touch the data itself. So what's the value of this? Number 4. What's number 4? Number 3, number 5. So this number 5 means in the cell, number 6 cell, we have a gene expression of the number 7 gene, have an expression level of 5. So what's the name of number 7 gene? It's here. The C16 open reading frame 13. So it's unnamed gene, basically. If you browse through, you see gene number 17 have a high expression level on average. Can you see this?
Yep.
Compared to the gene above and the gene down. And if you want to, you can plot CX, I want the number 7 gene, all the cells. So this whole row has been get out. And I can see plot this. Well, let me do that again. So that's the gene expression profile for this gene across 1,567 cells. And then we can see in cell number 922, this gene express level really high, 58, 52. And there's another higher peak. Okay, there are a lot of heterogeneity in there. If it's not easy to handle. If I hold on this plot, I will print out the number 18 gene and the plot on the same figure. Show print plot. Okay, you have a comparison of 2 genes expression across cells. So the right curve is from a number 18 gene, and the blue line, blue curve is from a number 7 gene. Okay, did you get this?
Yes.
Yeah. So this is the kind of way you can do this exploratory data analysis. Just give it a try and plot them out vertically, horizontally. Look at the correlation between them. Maybe some of these genes will also co-expressed if the cell have a high expression of this gene and another gene also have a high level and follow the same pattern. And this kind of exploratory analysis is very important. And most of the time, people don't do this enough. Because every matrix generated from real data will be different. And it was trying something like this to figure out the relationship between genes. And this gene is almost expressed in all the cells, no zeros. So you'll be wondering what's the number, this gene number 93. So I can do gene list number 3. Okay, this is a COX4I1. It sounds like it's an important gene. So if you really want to know this, and it's probably in the respiratory chain, you can Google the gene and then look at the name of the gene. Okay, so this is a cytochrome C oxidase subunit. So this on the oxidase complex is one of the components. And this expression is really high in this sample. Okay.
Yep.
So I'm going to close all the figures. Then I'll try something else and want to plot, say, X, then my 1. So anyone can tell me what this figure will be? What's the meaning of this?
It's going to plot X onto the y-axis. Maybe?
Okay, so this operation, say column, then 1 will pick the whole column of number 1.
Mhm.
And plot it out. So what's a column? Each column is a cell. So and here I'm plotting number 1 cell for its gene expression level of all the genes. Okay, so this is the number 1 cell's profile. Which gene expression level is the highest? It's this one. So instead of look at the matrix work horizontally, row by row, now I'm plotting column by column. So this gene, 8,5,16. So gene list 8,16. This is the most abundantly expressed gene in this cell, in the cell number 1. Is this housekeeping gene? By value, this is the highest. And this is the second one. This is immunoglobulin gene. Okay. So can anyone tell me how to plot a profile for cell number 11, for example? What's the code that you should use?
So do you want me to like type it in chat or just like?
Yeah, you can, yes.
Okay, I think it would be. That maybe?
Yeah, exactly. So I want to keep this here. I want to do a side by side. So I will instead of plot this directly, I will bring up a new figure. So this bring up a new window, small window, and then plot this. So if you look at these two cells side by side, they're different, okay? So for cell number 1, the first gene is IGLC2, but this one is not. The highest is this. And the second highly expressed is IgHM, but this one maybe not. It's different. Okay. So you can do this for every single cell, each cell has its own unique fingerprint. You don't expect them identical because they are unlikely to be identical, but some of them will be more similar to each other compared to others. So if you let me to visually detect similarity between profiles, I will put it this most similar to this, and this will be another place. Is that right? So my cell number 1 is most similar to cell number 12. And then my number 11 is distant away from them. Just by looking at their profiles.
Yeah.
Yeah, so exactly. So we can just compare their profiles and build a relationship between all the cells. If they're close enough, we put them together. If they're not, we put them away. So to make different subgroups. So we can do this with a smaller number of cells, but not 1,500 like what they're doing here. So that's why we need some functions to help us. What we can do to do this scatter plot, and then I take X in and the gene list. So that's all we need to give to this function. Okay, if you get this, let me know.
Yes.
Yep.
Yeah. So this gives you the information of a dimension of this data, and we have 8,400 genes and the cells. In this plot, there are 1,567 points. Okay. They all belong to the same category. So group 1, because I haven't started yet to subgroup them. So I just randomly put their relationship in the hairball, and then to see, okay, this is a group of cells I'm working on. So now I'm going to compare each cell to each other, just like what we did. We visualize the profile of the gene expression of all the genes. And then if they're similar to each other, put them together. So I'm going to do this called embedding. So if you can see the icon here, this one, I'm going to do my embedding. It will ask whether I'm going to embed your cells. So we are going to relocate the cell in this 3-dimensional space. If they're similar to each other, I put them together. If not, I put it in another group. So that's called embedding. You click yes, there are 3 different methods you can use. I'm going to use the first one, but you can feel free to try another one. You want the result to be 2-dimensional or 3-dimensional. It's up to you. And you just wait. Can you hear the computer is doing this this heavy job? I have my desktop, and the desktop still takes some time to finish. So it took me 25 seconds to finish this embedding. And remember, you have a selection of a row of these small gray icons. And then one of this is you can select and highlight. This allows you to do the 3-dimensional rotation of your data points. Let me know if you are ready.
Yep.
I'm ready.
Do you use the same analysis to get a similar shape, what I have here?
Yeah.
Okay. So let's look at this group of cells. They are clustered together, and these two cells have a very similar profile on average compared to a cell, this one compared to another, okay? So they are clustered by the distance, similarities. Okay, you have options to change the color, okay? This button here. You have options to change the types. If you have more cells, you want to see them, you may want to use dot. You can switch between 2-dimensional display versus 3-dimensional. Okay, 2-dimensional. Or you switch back to 3-dimensional. Okay. What do you think? What you can do with this? Any idea? By the way, if you click on the button and found a problem and any bug, and let me know and take a screenshot and tell me how you did it, and the program just crashed, I will fix it because I want to make this really robust. So far, so good. We don't have any error message, right?
Yeah, so far so good.
Okay. So what do you think you want to see?
I'm honestly not sure.
What other question you may ask?
I don't know. I mean,
Yeah.
all of this kind of analysis is pretty far beyond anything that like these sort of graphs are pretty out of my depth.
Yeah. Yeah. Why just give it a try? Let's see. If you click the first button on the bottom line and see what you want to get, and this tell me what you see. Just give it a try, and if it's crashed, you just restart this. So it doesn't matter.
If I push it, it gives me a pop-up that says show expression of single or multiple genes.
Okay. So what do you think will be useful? Did you get anything? Which gene you want to look at?
I don't know.
I'm looking at gene AAED1.
Okay, I just select this and click OK. And this, what do you think this tells you?
The frequency of the gene throughout the plot.
That's right. So, so these two subplots give you similar information. There's only different is this use a heat map. So you see the expression of this gene by its color. If the gray means there's no expression, if the red is the some level of expression. And similar here, but just use this bar plot. The higher expression have a higher bar. Okay. So this gene expressed in 18% of cells. So we have a 293 cells have this gene expressed, has been detected. So the value is greater than 0. And the cells express this gene are distributed everywhere. Basically, you can see from this population. Okay. So that's the information we can get about the gene expression of this gene among the cell populations. So you can do this for any genes you selected. So I want to give you a couple of minutes to find interesting genes. Can you see any of the gene look interesting by its pattern? If you found anything interesting, let me know.
Okay.
So my question was, can you identify some interesting genes show interesting patterns? So what we mean by interesting is something characteristics. So one way we can find whether there's a gene highly expressed in this tail, for example, that I use a method to find this gene called TMSB4X. It's highly expressed at the tip of this funny shape. So there are a group of cells looks very different from other majority of them and make this long tail. And I want to know what gene whose expression contribute to form this tail. So I use a method to identify TMSB4X is one of these. It's highly expressed in here. Maybe lowly expressed. I'm probably wrong.
How did you select a specific group of cells, like at the tip of the tail?
Yeah, so what I can do is you see here, can you see there's a small icon like a brush?
Yes.
So if you highlight this, it allows you to drag and select a group of cells.
Gotcha. Thank you.
Yep.
I think I missed a step because all of mine don't have that kind of swirl. I had to maybe download one of the toolboxes to get to the graph, so I was a little bit behind.
What is the figure you have? It's a hairball. You don't have this? Do you want to share your screen so I can see?
I just have the very first thing up, like the original figure. I found where I can select different genes. I just don't have them in the same configuration.
Yeah, so you need to press this button and then found a way to so-called embedding. So
Okay.
And then you select one of the method. We use this, but you can certainly use a fate or something else. Yeah, so I just gave you, I think this is enough for today, and they give you opportunities to explore those buttons yourself. Don't worry, and you won't kill the whole machine. And if you found any problem, let me know. By the way, some of this function you need to have R package installed, but not many. So give it a try. And for instance, I'm going to cluster cells into different groups. Yeah, so in this way, I use an algorithm to do this clustering analysis to separate cells into different groups. All right. So this is a small data set, only have 1,500 cells. In real application, you can easily have a data set, have close to 10,000 cells. 10,000 cells will be loaded into the memory and fill up your memory, and a lot of operations will be slower and you will realize like this embedding may take a couple minutes instead of just very quickly get the output. But that's something you don't have to worry at this moment. There are algorithm development method and the computational approach to solve this problem. You may want to buy a better computer to do this. Oh, by the way, you see a lot of these windows, you have this small camera here. And any this place, you can click this camera to take a video snapshot for your data. It will start to rotate your data automatically. And then at the end, you will have an MP4 file, and which is a small video capture the movement and to display the shape of your data points. Okay, so this will facilitate your share of information with your colleagues, with your roommate, classmates. See, I have a data which looks like this, and can you figure out why it's highly expressed in this group of cell, but not that? So this kind of a facilitation for the change of information between co-workers.
Okay, sounds good.
And some of these functions are newly built, like this constructed regulatory network of the gene. So if you click this, and then select some of the genes, and then you end up with a regulatory network, and then between genes. Okay, there are different buttons you can select. Change the font size, different layout, the network. Okay. So those functions are newly built. The student, your classmate from the previous group, at that time they don't have this, they didn't have this function to play with. All right, I will leave the rest 15 minutes to yourself, and I'm here for any questions